So I would like to, this is work with Silvia Papalardi. We are finishing now, and we are also continuing. So we are trying to understand a bit better the bounds that quantum mechanics poses on systems at low temperature. So the history probably is the bound of viscosity was the first that was discussed, which says that your system has to be at low temperature more viscous than something. I will give you an example. And the celebrated bound to the Lyapunov exponent tells you that your system has to be less chaotic than something at very low temperature. So as far as I know, there is no proof for the first one. And for the second one, there is a proof which relies on analyticity of the function of the related to the commutator, which helps to describe the Lyapunov exponent here. But it's a proof that although it is not horribly difficult, it is not so eloquent when you read it as to how the mechanisms of quantum mechanics act, at least to me. So let me give you an example, a very quick example. Imagine you have a system of hard particles and you consider first a temperature larger than 0 and you're doing a shear experiment. So these are as usual, you stick some spheres on the wall so that you create a rough wall, and you understand why there is viscosity. Because of temperature, the particles are banging against one another and exchanging their momenta and then banging against the wall. And in this way, transverse momentum is transmitted, which is viscosity. Now, if the classical system is taken to 0 temperature, then the particles are just sitting there and not much happens. And you can see that you can easily move your walls and nothing happens. So classically, you immediately infer that viscosity wants to go to 0. But remember that the bound I mentioned before tells you that viscosity has to be larger than something. You can understand very well what's happening, at least qualitatively, because when you are doing quantum mechanics, now you know that you have wave functions associated with the particles, but you know that wave functions don't want to be squeezed. The moment you squeeze them into a space they don't like, you immediately pay with some energy. So a quantum repulsion is induced between particles, and now you cannot move the walls for free if quantum mechanics is on. So here it is quite simple to understand, and this is something I would like to emphasize, the in a sense elementary nature and general nature of this discussion. So we wanted to understand a bit better these situations. So consider we will do something non-fermionic, because our idea of landscape is more naive for a bosonic model. And we want it to be interesting from the point of view of the bound at low temperatures. So immediately we realized that models like this one will not be interesting at 0 temperature, either because it's a crystal or because there is a minimum, which is the same thing, because quantum mechanics kills all your motion. When you get to very low temperatures, nothing moves much. And of course, the bound to chaos, for example, is respected, and the bound to viscosity too, but it's trivial. So in order to make something that puts a bit of difficulty to the bound so that it does its work, is to consider a system whose energy is flat at the bottom, so that there is life at very low temperatures, in the sense that the system can move around at very low temperatures. So you are naturally led to considering things that are like this, and this corresponds to billiards, where you have motion at any possible energy, or free motion on manifolds. And I remind you of Nonnenmacher's talk, where he discussed both together. These have been more than extensively studied. But here, rather than mathematical simplicity, what drives us to this is that we want the system to make the bound do something interesting, and we are forced almost to consider these. There are more cases than these, but these are the most natural that come to mind. So a comment that I cannot stop myself from making is that Arnold made, in fact, in his book, is that billiards are just like balloons in the deflated limit. So if you have a manifold, which is a balloon, and you take all the air away, this heart becomes flat and you get a heart billiard. So billiards and manifolds, billiards are just a particular case of manifolds, both classically and quantum mechanically. Okay, so now we have a manifold, and how do we define it? Well, through its Riemannian geometry, which is defined by how we measure lengths. This depends on the point. And we know that if lengths are defined this way, and we minimize this, we're going to get geodesics, because we're going to get the shorter path between points. And this is the Lagrangian, and this is a Hamiltonian of a free particle on these manifolds. Let me say from now onwards that I will consider a radius, any sum measure, so that all the G's will be adimensional in the future, and I will extract one representative length of the problem, so that all the rest is going to be adimensional. So what do we know about these? And what we know is that trajectories, if you minimize the Lagrangian or you minimize this thing, in fact, you get the same trajectories in real space. So what happens is that you are walking on geodesics, and energy only decides the speed. This is all classical for the moment. So trajectories are along geodesics. Energy is just the speed with which you walk over them squared. And quantum mechanically, you can extract a factor, everything that has dimensions outside. Remember that I considered this R so that I could have all my dimensions together. And this is purely adimensional, and it is the Laplace-Beltrami operator. In other words, this is as similar to a free motion you can have quantum mechanically on this surface, and everything that is physical and has dimensions is here outside. And when you multiply the data by the temperature, as you're bound to do, you find that it is this factor multiplied by beta is just the thermal de Broglie length divided by your characteristic length squared. So this is perfectly well, it has a perfectly clear interpretation as the quantum length divided by the typical curvature or radius of curvature of your manifold times a Laplace-Beltrami operator, which is adimensional. So this is particularly simple situation, and of course the same happens with billiards. Now we would like to be able to do macroscopics on this. So how do we picture a macroscopic billiard? When I say macroscopic, I don't say a big billiard, but I take it as a billiard for which I have a notion of thermodynamic limit. So here you have the most famous macroscopic billiard. It is just hard spheres in a box. So from the point of view of the spheres, it's many-body, but if you consider a point in phase space representing the collective, in configuration space, representing the collective positions of all the spheres, you are in a polytope in d times n dimension, the dimension of the space times the number of particles. And this has a particular geometry, and what you are doing is a billiard in this space, dn dimensional space. So this is, and the reflection rules along the walls of this polytope are indeed subsuming the reflection properties of any two spheres or spheres against walls. So this is a billiard, but the good thing of it is that we have a notion of thermodynamic limit. And another nice thing is that immediately we see, because we happen to know this from people who do packings, that some of the directions of this polytope can be arbitrarily long. Of course, in the limit where the box reaches the thermodynamic limit. So this means that whatever my de Broglie length, I will always have some degrees of freedom that are still wanting to be classical. And this is it's going to be very important. So it is not true that only mean field will do interesting things for you. This model, I will claim, has interesting properties at zero temperature. Another model, but this one is more like a manifold, which is actually macroscopic, is to consider spins on a lattice, Kagome lattice like this one. The spins are constrained to be each one on its little sphere. And we make a constraint that says that all the spins within a plaquette are sum up to 0. So you see that you have a space with many dimensions, and you have, I don't know, 5 halves of n or something like that constraints. So you have a large number of constraints that define a manifold in many dimensions. And so we have a system that is at the same time a manifold, a very well-defined manifold, and at the same time a system of condensed matter with the thermodynamic limit. So I warn you about, there are 2 papers by these gentlemen who have studied this. It's a little bit different from what I'm going to say, because this is more like, theirs is more like a phase space situation where your manifold is both momentum and coordinates. In the one for simplicity, although I believe it's not very different, we are going to consider a case like that. Well, discuss, because we're not going to consider that. Okay, so take hard spheres and consider the bound to viscosity. Well, you can write everything and you realize immediately, just because the way the units enter the problem, that when you write it in a form like this, which is when you want to do the bound, you get classically, very quickly, a result like this. A quantity with dimensions times a function of the packing fraction, which the packing fraction tells you about the geometry of the system. So it's the volume that is occupied by spheres divided by the total volume. And you get this factor t to the 1/2, which is normal because particles are moving at a speed that is t to the 1/2, and they exchange their momentum at that rate. So this is the classical, but you can also do the quantum mechanical, because you also have this factorization, the form of the Hamiltonian has all the units outside, and you find that the entire curve of the quantity you want to bound is an exclusive function of the typical distance, which in this case could be the distance between any 2 spheres, or the radius of the spheres, divided by the thermal de Broglie length, which is the de Broglie length at that temperature. So, so what you get is that this estimate here has a classical result, which corresponds to this one, which is linear, but it cannot be true because it hits against a bound, and it would tell you that you're going to 0 in viscosity. So somewhere the bound has to say, quantum mechanics has to tell you to stop and rethink your situation. And this happens when this length is of the order of the de Broglie length. And for example, this is the typical estimate that you make for the superfluid transition, but need not be only that. And now let us consider the Riemannian manifold. And what I would like to convince you is that automatically you have Planckian behavior, by which I mean that there is only one time scale, and the only time scale of your problem is the thermal beta h bar time scale. So first of all, what is transport from the point of view of a pure manifold? Well, transport is, you can think of it a little, and you conclude that you could define transport in an abstract way by saying that it has to do, or maybe defined generically for a manifold, as how many times a system spontaneously, by its own noise, turns round a handle in your manifold. This is easy. I mean, the simplest case you know is when you have particles in a ring, and the diffusion around the ring tells you what the conductivity is. Well, here it's the same thing. So this is the generic, if you want, way to define transport, such that you can also have a notion of transport within any manifold. Okay, and what about the Lyapunov exponent? So classically, what you have is that along the surface, you have geodesic lines. Now, the geodesic lines separate, and they separate exponentially. So this is like a chaos result, but it concerns geodesic. This is called geodesic separation, and is something that general relativists like. Now, what happens is that you are moving along those geodesics at a speed which is basically the square root of your energy or the square root of your temperature. And so your Lyapunov exponent is the geodesic separation times the speed with which you're walking along your geodesics. And it is simply the purely geometrical factor of the geodesic separation times the speed. And so you get, again, a square root behavior. This is classical, I remind you. And that's what it is. So this is very simple and also very natural. Now, when you write the actual Hamiltonian, it always has this form, as I said before. And so now it's an I-dimensional Laplace-Beltrami operator, and times all the units, everything that is important is here. So the typical Lagrange, the Lyapunov separation is something like the radius that your manifold, your smallest, the inverse of the smallest curvature your Hamiltonian, your surface has. And when you write things with the units of, as if you were trying to do the bound tells you that you have to stop there. But your classical estimate, again, just like before, hits against the bound when exactly at the level, exactly like before, at which the typical distance of your problem becomes of the order of the thermal de Broglie length. So something must happen at that length, because otherwise the bound is violated. In conclusion, manifolds, in manifolds, things scale like the bounds, in the sense that every quantity that is bounded by, I don't know, 2 pi, 4 pi, etc., is in your problem order 1. It doesn't contain any units. Semi-classics automatically makes you violate the bound. And now the question that evidently one asks is, okay, very well, all this we know, how does quantum mechanics intervene? What does it do? So with Silvia, we studied a very simple model. It's a mixture, a kind of beast that is a mixture between the hyperboloid, the hyperbolic surface of constant negative curvature, which has been very, very studied. And I highly recommend this physics reports of the 80s, which is very beautiful, of Balázs and Boros. And we did, for purposes of understanding it better, we stuck to it a cylinder which is entirely trivial from the point of view of chaos. It's like as if it were flat. And now you move along this surface, you move along the cylinder, then you enter the hyperboloid. That's where things become interesting. Then you exit them, then things become uninteresting. Then you bounce on the lid of the cylinder and then re-enter. And so your Lyapunov is simply the Lyapunov you would have in the hyperboloid times the fraction of the time which you spend in the hyperboloid. And well, this is the Escher picture of bats, which you all probably know. And here you have the Poincaré disk, which is the hyperboloid. It's a representation of the hyperboloid. This is a trajectory that enters the hyperboloid. We're not putting the cylinder part. And you see how the same trajectory enters and exits and then re-enters in another point, and you get a nice Lyapunov exponent, which is, it takes exactly the value, there is no fit there, exactly the value it has to take. So 3 mechanisms for the bound to act. The first one is trivial, and I will say not much about it. Imagine that the cylinder has a small radius, like this, and that the wave function is large with respect to it. Or imagine that in the spin models, you're moving on a sphere and your wave function is long with respect to the size of the sphere. This is a clear case where quantum mechanics will stop you from doing things. For example, in this case, when the wavelength becomes long enough, then you can approximate the whole situation with lower harmonics and you're back to a finite spin quantum system. So it already is not going to be very interesting. So this mechanism for stopping you from being chaotic exists, no doubt, which has to do with the compactness of directions of a manifold, but it's easy to understand. There are two mechanisms that are a bit more difficult to understand, and they are perhaps more interesting, is the following. These are the equations for the motion for the Hamiltonian in the hyperboloid and in the cylinder. So don't look at them very much. I'm just showing you what they are. Don't look at them very much, but now we transform them into a way that we can understand better. And what we find is that this looks like a Schrödinger equation, but notice what has happened. A constant factor plus a kind of centrifugal potential have entered the game. The centrifugal potential, I'm not so interested because it drops down to 0 very quickly. It's a hyperbolic sign. But this is a factor which gives you a step function in an energy. This factor exists within the hyperboloid, but it doesn't exist, of course, within the cylinder. So the system thinks that it is doing a normal Schrödinger equation, but it hits against this step, whose height is proportional to h bar squared. So it is not purely classical, but it's a long step and it has all the properties of a step. So if you do waves hitting, this is the part of the hyperboloid, this is the cylinder, when the energy is fast, so you're in a very WKB context, semi-classical context, nothing happens and you're okay, and you get the classical Lyapunov exponent. However, when you go down in energy, you reach a point where your plane wave hits this effective step and just becomes an evanescent wave in the hyperboloid. So the region that was chaogenic, just to coin a word, is forbidden now. And the same you see here. And when you put all things together, what you discover is that for our system, because of this fact, this is what happens. When you plot, as usual, in terms of the typical radius of curvature of the hyperboloid divided by the de Broglie length, and you move into the quantum region, before you hit the problems where you are having troubles with the bound, your system begins to have this kind of trouble. And first of all, when it gets to the step, it moves slower. And if the energy is low enough, it doesn't enter at all. So this is okay. And this explains how this has saved the bound from being violated. There is another effect, however, which is even more strange. Consider a packet that is moving on your surface. This could be any surface, but we did it in very great detail in ours because this one is very easy to compute. And now you calculate the distance measured, of course, with the appropriate metrics along the that separate two trajectories. But now you're firing a packet. So you go to Wikipedia on semi-classical packets and you discover that, well, it has a linear term. So when you calculate the average of the separation, it will have a linear term in the exponent, a constant term, a linear term, which is the Lyapunov expansion you expect. And then it has a quadratic term in T. And this sounds very strange. It is growing faster than an ordinary Lyapunov instability. This was for us a surprise. But now the point is you say, okay, very well, but I would like to interpret this as a Lyapunov exponent. So I would like this term, the linear one, to be dominant over the other two so that I have the possibility of interpolating an exponential growth or defining, for that matter, an exponential growth. So when you may put all these inside for a packet, you discover that you can only have this if something very similar to the bound, of course, without the 2 pi's or anything, but something of the order of the bound applies. Otherwise, there is not even the possibility of defining a Lyapunov because you have something that has a constant separation, which is already large, given by the initial size of the packet, And it has a very quick and eventually fatal expansion that goes like t squared. So already here we have three mechanisms which we can, and they all lead to the same bound. It is a bit embarrassing that it seems that quantum mechanics has a diverse bag of tools to do this, but it seems that this happens this way. So very quickly in the 5 minutes I have left, yes, but there is a problem. We decided that this was how the bound was saved, but we are not approaching it at zero temperature. We are being killed before we reach it. So one natural thing to say is, okay, so let me consider several radiuses and make them softer and softer, and so that I have different possibilities to approach more and more the bound. So this is what we did. We considered this system now, which is a cylinder with a soft, or let's say not so curved hyperboloid and a very curved one. So the first one acts from the beginning, and this tip creates the biggest Lyapunov. Then there is another one that creates Lyapunov that is smaller, but as you will see, it survives more to lower temperatures. And then we have the cylinder that does nothing. So we have wave functions that are semi-classical and use the two, and that's okay. We have wave functions at lower energies that do not enter the most chaogenic part of the cylinder. And at even lower temperatures, we do not enter either of the two. So this is the way to create artificially this situation, several stages. So what I want to say by this is that many scales are necessary if you really want to approach the bound a bit better, up to the end. And so maybe almost to conclude, this is a very nice example where this happens. These are spheres in a amorphous packing that is very close to random close packing. So it is almost in random close packing. So when you look at what the spheres can do, this has been studied a lot by people who do random close packing. It's, as I mentioned before, a polytope that has distances, or if you want, frequencies of vibration of all sorts, meaning that you have from the highest, which is given by nearby particles colliding, to collective motions that have all possible time scales up to zero. This is known for an infinite system. And now what happens? I turn on H bar, but I know that H bar doesn't like to get into narrow regions because wave functions will kill regions where you're forcing them to enter something that is smaller than the de Broglie length. In other words, you will pay with energy. So at each level of T over H bar, you will be killing the things that are more thin, but those are the ones that give you more chaos. Remember that omega is an inverse time scale, so it has the same units as the Lyapunov itself. As you move to more and more quantum system, you are losing, you're killing by quantum death, more and more degrees of freedom, but you always have some. And what seems the natural interpretation is that the winner, which is the one that is just about to die from quantum mechanicness, is the one that gives you your Lyapunov, because it's the fastest one without having been yet completely killed by quantum mechanics. And we expect something like this to happen in this model, but this is something we're working on. So to conclude, 3 points. Imagine that you have a system whose continuation of the high temperature solution breaks the bounds. This is very easy to do. I gave you 2 examples. Something, then you know that something is wrong with your semi-classics, and you know where it is wrong, the point where you hit curvatures, where your de Broglie length hits curvatures. So now you know something about the system and its quantum mechanics just by knowing that the bound exists. Now, it's very easy, and I showed you just now, how to construct a good scrambler, somebody who has, for example, for the Lyapunov, the good units. But I didn't tell you, because I don't know, how is it that I can construct this way something that really saturates the bound like SYK does? And this is a question that is open, I think, at the level of this kind of description. So you get the right units, but not the right 2π. Another point is that this, I think, listening to Stefan Nonemacher talk, the stage is set to consider both bounds in manifolds by mathematicians. They know more than us about these things, and they have a simple or relatively simple model and family of models where these things could be done. And my advertisement for the topic is that this is a nice topic of general physics. Although it was born in the context of black holes and things like that, this is general physics. So this is personally why I like it. So that's all.
Thank you, Jorge. So we have time for questions. Okay, maybe I can start. So if I understand well, so what you say is that if you take like packing close to jamming and you switch on H bar, then you get a fast scrambler, not maybe, okay, a fast scrambler because you have this isostaticity that kicks in.
Yes.
But you are not, you don't know if the 2π you get
no.
with 2π.
No, but I know that it will be non-trivial in the sense of approaching seriously the bound, let's say. Not 2π maybe, but it could be 1, let's say.
But I was thinking, because when you take those packings, it's true that you have this long wavelengths, but you have also like, I mean, in large dimension, it's okay, you have just this long wavelengths. But when you go to finite D, you also have like bucklers somewhere.
Also.
And do you think that those local effects can change, maybe put a bound that is not the best one?
No, I think that they don't help you because a rattler is a particle that has a little cage, a private cage of its own where it rattles. Now, the cage has the size. At the level of H bar, when the de Broglie length becomes of the size of the little cage, the rattler is dead, and it's dead. So it won't give you, it will give you a Lyapunov at lower values of H bar, but at that specific level of H bar, it's dead. So because it just cannot rattle anymore. So it will die at a certain value of temperature, if you want.
Yeah, I was not thinking at rattlers. I was not thinking about bucklers that are still spheres that are like in this isostatic network. So they enter into the macroscopic rearranging region, if you prefer.
Yes.
But they are within the network, so they are not really like isolated rattlers that are killed. So that's
okay. So in other words, what you're asking is a bit the general question. These long sides of this polytope, when I see them in physical space, in 3D space, how does it look, and what can I conclude of them? These are the last to die at low temperatures, and they are giving you all the chaoticity you have at very low temperatures, and it has to be very collective. I would like to prove that you need collectiveness to have approaching the bound for a macroscopic system, for the reason that you imagine that you need the motion to be long, but to be long in phase space is you need a collective motion of many actors. And I firmly believe that you need that.
Okay. Are there other questions?
I can ask. Bye, Anatoly, go ahead.
I would like to ask a question about reaching the limit of 2π.
Yes.
If I understand correctly, this is what people call the maximum chaos.
Yes.
And maybe I'm missing something, but I thought the only examples of maximum chaos are large N models which admit some form of holographic description.
The ones that are known, yes, absolutely.
So my question is the following: if you hope to approach this limit, do you also expect those models to be holographic in any sense, and if they have large N in any way?
Well, this is very diffuse, but imagine that one does, and we are going to try to do some form of approximation to calculate the situation in this packing. And well, one possibility is that the limit is pi/2. Well, okay, that's not ideal, but it's a good thing because it reached parametrically the good thing. Now, if we got to pi, then of course we would be looking desperately for some form of holography playing a role there. There is a kind of scale invariance in packings in any dimension, amorphous packings, because the kind of motion that they have seems to scale. It is power law in everything in distance. Now, will it be holographic? Well, that I cannot say, but it would be fantastic if it would be true. But at this stage, we're not as precise as that.
May I just ask for a clarification for the question, even maybe also a helpful point? Totally, I thought we know that this maximal Lyapunov exponent comes from the symmetry breaking, meaning the leading description being a hydrodynamic one that's given by the Schwarzian mode. So this of course is much more general than holography. So having a maximal, I think the statement that the maximal Lyapunov exponent is strictly related to holography is too strong. Or
yes, that I mean, because if your sigma model is the Schwarzian model, okay, but do you really need? Maybe it's the case, but is it a fact that you need necessarily to have that your system is described in the infrared by a Schwarzian theory? Is this a necessity? I'm not sure. Maybe it is, and I don't know it. But surely the two cases we know that work, they work that way. But I don't know.
No, but my point was a different one. I mean, I think I also agree with the point that you're now making, which is that it's not necessary, or we don't know if it's necessary. But what I'm trying to say is that certainly we don't believe nowadays that a holographic dual is necessary to have maximal scrambling.
Okay.
But having an effective Schwarzian mode description is some form of holography. That's simply a holographic description of some low energy modes. You might not have.
Well, I think that's. I don't necessarily agree with that, because I think it's a question of the symmetry breaking scheme. It's really as robust as the symmetry breaking. But anyway, maybe we're getting into. We should discuss it at some point, Tolia.
Okay, Marco, maybe you wanna ask a question?
But if you have time, yes, maybe. Jorge, just a question about, so you had this plot in which your Lyapunov with a bit of quantum was getting close and then was going down. Can you, can you repeat? I missed, what is the mechanism that brings it down?
So, yeah. So you're meaning this one?
Yeah, exactly.
Okay, so in this case, so this is the hyperboloid part, and this is the cylinder part, and then you have a wall, no? So what the curve here, this region is the curved one, this is an axis, no? And this region is not curved, no, doesn't have a mean. So what you find is that this produces an effective potential to you that is exactly the radius of curve, the inverse curve radius, so the curvature of the potential. So what happens is that of the manifold. So your wave function that it goes that way meets this thing, and it is
okay.
And it runs into this thing. Now, if its speed is large, nothing happens. If it's smallish, it may be able to hop on top, but it will lose some speed in doing it. So it will lose its Lyapunov, because we said that Lyapunov was proportional to the speed. And so this explains this twist in the curve. And then there will be a moment where you don't even enter there because it's too low energy. And then there's nothing happening because you stay in the cylinder, which is completely uninteresting.
Okay, yeah, thanks.
Okay, so thank you very much, Jorge. And yeah, we